All right, good morning, class. Today we'll continue where we left off last meeting. What's the last thing that we discussed?
Transist transistor, sir.
Okay, what about transistor?
Katong tulo nila ka kwan sir katong
Tulo ka
emitter
ah,
emitter
emitter, emitter lang. I think you're referring to the three terminals, no, of the transistor. Okay, correct. That's good. Rex and um, Carl, nasa chat box. They said that the transistor has three terminals, of course, the base, the collector, and the emitter. No? Base, collector. Di na siya connector. That should be collector. Base, collector, and emitter. Okay? So, we've also established that transistors, or more specifically BJTs, are used to, or are used in circuits that could somehow amplify signals, whether it would be sound or whatever kind of signal there is. Okay? So to design an amplifier, okay, there are two parts. Okay, the first part we've introduced last time. So there are two portions or two parts on how to, or yeah, how to do or how to perform analysis and design on amplifier circuits of BJTs and transistors in general. There's the DC portion or the DC part and the AC part. Okay, so last time we've introduced the very first configuration in designing or in establishing the DC analysis of transistors, and that is the fixed bias configuration. If you remember, it looks like this, or it somehow looks like this. Okay, this one. So this is our transistor or BJT. It could be characterized by its parameter, DC current gain beta. This would be our source, VCC, our resistors, RB, and RC, because this is the collector, and RB. Okay. So as a review, somehow, how many loop equations could we do or could we extract from this configuration? Now we could redraw this circuit so that Marshag somehow circuit that we're familiar with. No, we could redraw this one into a circuit that looks like this. We separate the DC sources and somehow atong i-bend ang wire. No? Bend to the left and bend to the right. Okay. So that the loops are more obvious. Okay. So this is the same circuit or same fixed bias configuration as the one on the top. This is our source. This is our resistors, RB and RC. Okay. So the loop equation that we could extract from this one is from the first loop. So review ito niya, ito na may na-cover last time. IB, RB minus BBE is equal to 0. And VCC from the other loop minus ICRC minus VCE is equal to 0. Now, could we immediately solve for the unknowns from this equation directly, or we need other equations or relationships? Okay, no. So what are those? This is the fixed bias configuration. We have other configurations as well. We have emitter bias, voltage divider bias, source follower, and such. No? But generally speaking, whatever configurations we will be using, how many general relationships or equations that we have in order for us to solve specific equations such as this? Ilagay ito ko buok. 5, higher, lower. I think 4 is enough na siguro to. No? There are 4 other equations that we could use. 4 general equations for DC analysis that we could use to solve for equations specified by a particular configuration. So I could give the first one, or at least any one of these 4. 4 general equations that we'll be using when analyzing DC circuits of transistors. Now you could turn on your mic or you could type sa chat box. IC equals beta plus 1 IE. Is that correct, class? Okay. Ni Carl, VBE is equal to 0.7 volts. Okay, very good. That's the first one. No? I think dili ni correct ng IC is equal to beta plus 1 IE. No? Or the other ones. The KCL equation 1. Saman to. IE equal to something. IC is equal to something. IE equal to IC plus IB. Very good. Thank you, Jen. IC plus IB. Now, I think ang pasabot ni Maui is IE is approximately equal to IC. Okay? But we don't normally use this in analysis and design. No? This is a very crude approximation that is useful maybe when we're going to analyze switching circuits, no? But not amplifier circuits. It is good to know that we could approximate IE as IC. Okay? Another one is IC equal to beta IB. Very good. Beta IB. No? The last one, saman to, IE is equal to something. Okay, this is the one where IE is equal to beta plus 1 IB. No? Meaning, from out of these 3, as long as we could determine IB, makuha na nato si IC and IE. No? Okay. So let's try to solve, let's try to solve another fixed bias configuration circuit. No? Okay. Let's try this one. Given 12 volts. RC is unknown. RB is unknown. Okay. Or our beta is 80. Let's specify that VC is equal to 6 volts and IB is equal to 40 microamperes. Sige daw. So this is an example of a design problem. Design because unknown, si RC and si RB. No? Okay. So using these equations, ayan sila, BCC minus IBRB minus PBE is equal to 0. Okay, this is known. IB is also known. Actually, we could immediately get IC and IE because beta and IB are both known. No? IB is 40 microamperes times RB minus BB is 0.7. Okay, we'd like to solve. RB is how much? Okay, get your calculators. $282,500 ohms or 282.5 kilo ohms. So 282.12 BCC given. 12. Or di lang siguro klaro ang akong lighting. So 12 volts. Okay. Yeah, 282.5 kilo ohms. Lagi, 12 na siya. Okay. The next one. BCC. This equation, BCC minus ICRC minus VCE equal to 0. What is VCE? VC is given 6 volts. How many siya measure if you're going to use a voltmeter? This is the collector. No? So if this is the collector, from there na to measure si VC. Okay. Is VC equal to VCE? Yes or no? No? Yes? Maybe? Now, supposed to be si VCE is from this point to the collector, to the emitter. This one. This is the emitter. This is the collector. This is VCE. Okay. VC, again, for any given voltage na isa lang ang subscript, to measure it from that point, in this case, collector, to the ground. But seeing as the emitter is also connected to the ground, no? Okay, bali VE is equal to 0 kasi it's connected to the ground, no? Somehow we could ignore that one. We could say that VC is equal to VCE. So VC, which is 6 volts, is also the value of VCE. No? So for the other equation, VCC minus ICRC minus VCE, ICRC minus VCE is equal to 0. Yeah. What is IC? Okay. IB is given, beta is given. We directly multiply. IC is equal to beta IB. 3.2 microamperes minus Rex. Okay. So, sakto na siya. I hope. 3.2 microamperes. So, VCC is 12 minus 3.2 micro times RC minus 6 volts equal to 0. Therefore, RC is how many ohms? One eight seven five. Okay, correct. 1,875 or 1.875 kilo ohms. Okay. So, questions? Sandra? No, 3.2 is not given. 3.2 was calculated from the product of beta, which is 80, and IB, which is also given 40 microamperes. So, yeah, close to given siya. And the next question, okay, we've also determined that fixed bias is a not so stable, not so stable um, circuit configuration for amplifiers. Why? Uh, Although we plan to approve last time, but whenever beta will change, or worse, will increase, may change in value. Of course, we could say nga mag-change din sila. Change ang value sa ano, um, change ang value sa currents and voltages. Okay? Of course, these are fixed. So, supposing we draw our circuit, okay, same source, 12 volts, but RB is this one, the one that we've obtained, 82.5 kilo ohms. So, pag-drawing. And RC is 1.875 kilo ohms. Now, on your own, supposing due to wear and tear and increasing temperature, our beta has changed from 80 to, let's just say, 150 na. Okay, almost times 2. Okay. Try to solve for the values of the currents on your own. No? IB, IC, IE, okay, and VC, VCE, okay, and compare the percentage difference, okay, of the values for each of this one. Sige daw. Mga 5 minutes. Kidali naman niya siya.
Sir, pwede ipasakad gamay ang question, sir. Hindi kay klaro, sir. Or, yeah,
What do you mean?
like ang
Circuit?
maklaro ang para. Okay na sir. Tama.
Okay na? Okay. So the percentage difference would be okay, 200% times Old minus new over old plus new. 200 times siya. Okay. So, muna itong gamitin ng formula to solve for the percent difference. Para ito ma-compare, no? Let's compare how unstable our circuit would be. So the new value for IB is still the same. Okay, 40 amperes. Six. Would you agree na 6 milliamperes is the new value for our IC? Okay, 6 milliamperes. Of course, IE would be 6.04. No? Multiply laman ni siya og 150 and multiply ni 151 to get 6.04. How much for BC? How about for BCE? Did someone solve for the value of for VCE? Gamay kayo? 0.75? Same tag value? Kuan. 12 volts minus ICRC minus VCE is equal to 0. Okay. Follow ba? 12 minus 6 milli times 1.875 kilo minus VCE equal to 0. Would you agree with this value? Okay. So, sige. Let's try to solve for the percentage difference then. How about for IC? 200 times 6 minus 200 minus 200 times old 3.2 minus 6 3.2 plus 6 more or less negative 60%, 60.9. Okay, 60%, 61 more or less. How about for IE? $60 gapon, okay, 60%. Now for VCE, I doubt na 60% gapon eh. Old minus new. Yeah, old plus new. So 155% decrease, no? So grabe ka unstable. Now, there's a solution for this one, okay? Which would be the next configuration. We call that one the emitter bias configuration. So what do we do? It is said that this is a more stable configuration compared to the fixed bias, and it could be simply achieved just by adding a resistor on, or we connect a resistor to the emitter. So this is the emitter bias configuration or emitter stabilized. BCC, RC, RB, ano bali? RB, RC, and RE. This is still 0.7. This is still characterized by beta. Okay? Now, if we're going to derive the KBL equations then, so I'm not going to read out this one na ha. I think na-solve naman na to ang iyang equivalent na circuit. Pwede na mag-directly form our KBL equations. First, from this loop, okay? So we have VCC minus IBRB minus VBE minus IE/RE equal to 0. Unknown and unknown. For the next loop, the same. Ito mga agi. Just the same with the fixed bias, but with the addition of this parameter. Okay? VCC minus ICRC minus VCE minus IE/RE is equal to 0. So, yan na lang. Simple as that. So, let's try to solve an example using the previous one that we did, but with the addition of RE. Let our RB be the same, 282.5 kilo ohms. Our RC is 1.875 kilo ohms. 75. Okay. And let's say our RE is 1K. 1 kilo ohm. And supposing our beta is itong gamiton, 150 or 80. Say for example, 150 gihapon. Okay. Using KVL equation 1, VCC is 12 volts. 12 volts minus IB/RB minus 0.7 IE/RE. Okay. One equation, two unknowns. So, sa buhaton. What do you think we should do? Hindi natin na-solve. We have no value for IE. Di necessary mag-systems of equation because wala man si IB there eh. No? So you could not use systems of linear equations or simultaneously solving because this is IC. IB man eh. Diba? We've said earlier that these are the general formulas for DC analysis. So if we replace our IE with this relationship, beta plus 1 IB, this equation will be in terms now of IB. So solvable na siya. Okay, so nadagibutan ni Carl sa Thank you. Thank you, Carl. Nag-credit po daw si Rex. Okay. So, 12 minus IB, 282.5 kilo minus 0.7 minus IE is beta plus 1 IB. Times beta plus 1. 150 plus 1, that's 151. 1K equal to 0. Therefore, IB could be easily obtained. Sige daw. Okay, 2.6 to the power of -5, or i-micro na to, more or less 26.07 microamperes. Huh? Therefore, IC and IE could be solvable by multiplying IB with 150 and 151. Did you get the same answer? Okay. Next, BCE. BCC. Okay. This one, minus ICRC minus BCE minus IERE. So, dito na ako 12 volts minus IC is 3.9 milli times 1.875 kilo minus BCE minus 3.94 milli times RE 1 kilo. For BCE is equal to 0.7475 volts. Okay. Now, based on ng mga values, could observe that, well, earlier, compared to the fixed bias, beta is 80, most of the mga original, right? No? But if na-increase na to ang beta to 150, and we added an RE of 1K, so ang stable is, instead of obtaining 6 milliamperes without RE, somehow na stable ang IC and diba? IC and IE. From 3.2, even if na times 2 ang beta, no? But by the addition of RE, um, dili ra kay nga nakadako ang increase, no? Increase na siya og mga 0.7 milliamperes, no? Although ang VC is the same, no? 0.75 lagi apon. But at least nag-stabilize ang ICs and IE. Okay. So, pareha. Now, if our load is current sensitive, no? So, at least, the low, even though nag times 2, kibali ang atong kuan, nag times 2 ang atong beta, no? Yung 150. But, dili ra kaya nakalayo ang change sa IC. Okay? Observe ninyo or understand? So far, questions? None? Sabton ra? To answer the question ni Abun, need ba mag-add ng 1K? Yeah, if fixed bias siya, then gusto natin i-convert from fixed bias to emitter bias. Of course, mag-add tayo ng resistor, but hindi necessary na 1K. No, it could be any value. Arbitrary lang to sa kanina example ang 1K. But yes, to stabilize the circuit, no, so that it will be less dependent, no? Not really totally not independent na, but for it to be less dependent on beta for any temperature changes, no, for the degradation of the transistor, no, because when the transistor degrades or when temperature increase, beta will change or swing its value, no? An additional resistor to the emitter will increase the stability, no? So it's not necessarily 1K, but as long as there's a resistor sa emitter, no, compared to the fixed bias, the resistor to the emitter will be more stable. No? So I hope na answer ang question mo, Abun. Yun sa pag-solve ang IC. Sa previous example directly, Jeffrey, sa this example. Okay. Pagkuha sa IB, okay lang. Mani bago lang. Okay lang, no? So, this is how we obtained IB from this equation, no? Ang na-change lang is we replace IE with the relationship beta plus 1 IB. That's why IB is obtained. I-multiply lang si IB o beta. Mukha natin sa IC. Ay, nag-brownouts uptown. Okay, Jeffrey, no? Once IB is obtained, dali ra ma-solve na yung si IC and IE. Just multiply this one with beta to get IC, and multiply this one by beta plus 1 to get IE. Okay. So I hope that's clear. Okay naman sa we have that equation. Sige. Kanina daw. Let's try this one. 12 volts gyapon. Okay, on your own, solve for the values of all resistors. Supposing that we need our IC to be 2 milliamperes and VC is 7.6 volts and VE is 2.4 volts. Sige daw. 5 minutes gapon. 5 to 10. Ay, Mond, ang required di ay kay kuan RC, RE, and RB. Wala, nawala yung net. Nawala lang ko kadyat. Okay lang. Does anybody have a value for RC, RE, and RB? Nanin nakasolve? Spasa Raymond eh. Okay. I'll check ha. Dahil lagi nag-values RE ug RC. Check daw again, Mon. I think correct ni kay Justin. RC is 2.2. Sige daw, Mon. I-explain, maon mo mong cam. I-explain daw imong RB. At least sa RB lang. Okay, quick lang.
Ang RB sir kay gigamit to na akong equation nga VCC minus IBRB minus
Okay,
VBA.
ma-show ni mo imong kuan?
Ay,
Paper?
ambot ko maklaro siya sir.
Klaro man siguro, be. Okay. Medyo kuan lang ang cam, pero
Ako na lang i-kuan sir. So,
sige.
ang gikuha na ko ang IB first which is IC over beta. So, 2 milliamperes over 80. So, mo kuan siya 25 microampere. Tapos ako rin siyang gi-substitute dito sa equation nga VCC minus IBRB minus VBE minus IERE.
Mm-mm.
So, ang variable na lang nga nabilin is RB. So, gisolve na ko si RB. So, 12 minus 25 microampere times RB minus 0.7 minus 2.4 volts.
That's
Tapos napaday
why,
ko si Kwan, 356 kilo ohms.
Dabi, how about for our RC ni mo? Sige daw, i-dictate mo yung equation.
Ang RC sir, kaya ko rin
Sige, ba na?
ohms lura na ako sa tapulan kayo.
Okay, magdili siguro na siya ba?
Wala na ako
De,
gigamit ng second equation. Try na ako gamit ang second equation.
sige, kay Kuanda, how about Justin?
I-explain ang RC, sir.
Ma-show ni mo sa imong cam, imong paper.
Uh, Pero di man siguro maklaro, sir.
Try lang. Hindi.
Maklaro. Bal.
Di mo automatic siya balik kay maklaro man. Okay, so RC is equal to VCC minus VC over IC. Okay, okay. Given naman si VCC, si VC. Okay, so VCC minus VC over IC. Okay, that's why 2.2. Okay, very good. How about RE?
Ang akong
Given
RE, sir, is 1,200.
1,200. Okay, sakto, 1,200. Okay, thank you, Justin. That's correct. Maybe, sa to, gi-omso to ni mo, Rex, no? Gidiretso na sila ni mo divide ang 7.6 og 2. 7.6 divided by 2. Okay. Si Raymond eh. Si Raymond. So, dili siya directly because okay. Sige asa tong chat. So, correct tong answer ni Justin, guys, RC is 2.2 and RE is 1.2. If I'm not mistaken. RC is 2.2 and RE is 1.2. Okay. So, maybe nakuha to ni Raymond ginabi, common niya siya mistake. Even ako nag-perform ko po gani before itong student po ko. I-directly then i-divide to get RC. No? But remember, si 7.6 is gimeasure na siya from this point. Okay? This is the collector, again, the emitter, and the base. From the collector, if natin multimeter kibali, no, we would obtain a voltage drop of 7.6 from this point. Now, to get RC, or to get the voltage drop of RC, we should have the lens of our multimeter, ang isa at this point, and ang isa at this point, no? And we're here, or the other way around, no? Because if ang kaning VC, ang multimeter na to, or atong meter, ang one point nasa collector and the other one is a ground directly, no? So nasa 7.6. That's why we cannot get the value for RC simply by dividing VC and IC, no? Yan na. Okay na to, Raymond? You understand? Okay, sige. Kita ko na kayo mong thumbs up. So, it would be good if mag-KVL equation ta. Yeah, KVL, no? Loop. 12 volts. Para ko para, diba? Distinguish na to. VC is not equal to the voltage drop of RC or VRC. Ano na lang. Okay? So, they're not the same. No? Of course, they're the same. Sa emitter bias, VC is also not equal to VCE. No? So, if mag-KVL ta, we have 12 volts minus VRC, which is ICRC. KVL takibali dire. Again, remember that the 7.6 is measured from this point to the ground, okay, by the meter. No? So, if mag-KVL ta, igana. Okay? So, 12 minus VRC, which is ICRC, no? Minus VC, equal to 0. Yeah. So, 12 minus ICRC minus 7.6 is equal to 0. So, this becomes 4.4 minus 2 milli times RC equal to 0. And RC is 2.2. Yeah, 2,200 ohms or 2.2 kilo ohms. How about VC? VC, no? Maybe obvious man sa circuit that VC is just the difference of VC and VCE. Now, VCE is the difference of VC and VE. So VCE then is 7.6 minus 2.4. 5.2 volts. Okay, VC. Did somebody get a different value aside from 5.2 sa VCE? Any questions so far? Sa Enra? Ay, masa yun. Diode circuits or transistor circuits? Ohm's law. Wala pa din nato ito na-answer na tong kuan. Na-answer nato to puhon. Tomorrow siguro next meeting. Okay. So, ba challenging din yung kuan? Kani. Ang VBE ang 0.7 always. Lahi na bang VBE ug VCE ha? Okay lang. Heard yan ha. So VBE is constant na gina siya, 0.7. Kani constant. Kani is gina-solve. VBC is gina-ignore, no? Ano ganito gina-ignore ni because the base collector junction is reverse bias. Okay. So VBE is, yes, constant na siya. Now, another point of consideration, point of consideration is we should also know the saturation point of our circuit. Okay, so the formula for the saturation point of the fixed bias, do you remember? Say, formula sa IC saturation for fixed bias the other last meeting, no? Meaning the maximum value that the maximum value for the collector current that would flow towards this loop sa fixed bias. Okay. So this is a fixed bias man, di ba? So for a fixed bias configuration, remember sa characteristic curve, sa saturation, VCE is 0, no? So for VCE to be 0, we could somehow replace this one by a short circuit, no? Pwede natin i-short, no? Para directly 0. So the saturation current is, or the equation now, if shorted ang VCE, or VCE is equal to 0, no? Because maumani siya ang kuan, di ba? VCC. Fixed bias ni ha. Review lang ni siya. VCC minus ICRC minus VCE is equal to 0. But because we shorted VCE, this is 0, IC is directly equal to VCC over RC. Okay? And IC, this is the saturation current. IC sat is VCC over RC. Now, how about for emitter bias? What is the saturation current? No? So that we'd know, no? If ma-obtain na nato si IC, you multiply it by VCE, no? This one, and so that we could determine if close pa ba or layo ba to the point of destruction, no, ang atong transistor. Okay, di man magdepend ang power dissipation, no, sa saturation current sa atong circuit. So if for the fixed bias, the IC saturation is equal to VCC over RC. Now how about for a emitter bias? Ato short, okay? Same yapon. I-short na to si VCE or VCE is equal to 0. So ang atong equation then becomes VCC minus ICRC minus 0, no, VCE, which is approximately equal to 0, minus IERE equal to 0. Okay. So, dinadayin mo sulod itong other approximation na atong ginagamit, nga atong pwede magamit, which is IC is approximately equal to IE. So, these two are equal. Such that we could easily obtain the value for IC. IC then is equal to, equal na silang duha, so transpose to the other side, VCC over RC plus RE. So that is the formula for the IC saturation or the saturation current of this type of circuit, emitter stabilized or emitter bias. VCC over RC plus RE. Okay. So for this example, how much is the saturation current? Then our IC is, our operating current or our operating IC is 2 milliamps. How much then is our saturation IC? So just divide 12 over 12 volts divided by RC, which is 2,200 plus 1,200. 1,200 ba daw ito? Ano, si kuan ganina. Si Justin, I think. Answer siya ganina, 1,200. So, yeah. 3. Thank you, Lex. 529. 29 milliamperes. Okay. So, ito saturation current. Okay. So, layo pa. Question so far? And so far. Okay. Thank you, Jeff. How about the others? Okay ra? Sabtan pa? Okay, so the last amplifier configuration circuit that we'll be tackling this morning would be mas stable pag yun, no? If you compare it to emitter bias, no? Well, it's super stable compared to the fixed bias. We call this one the voltage divider bias. No? And later, ato ma-observe nga nung more stable pag siya. No? So, a voltage divider bias looks like this. No? So, notice na mo niya itong emitter bias. Diba? our source, RC, RE, and RB. No? To upgrade this one to a voltage divider bias, so not a voltage divider circuit, on the left portion of our configuration. So we just add an additional RB. No? So we call this one RB1 and RB2. So if we try to solve some examples, we'd know that much stable pag yun siya compared to fixed bias and emitter bias. No? Now, the trade-off then is may increase gamay ang complexity sa atong analysis. No? Especially sa kaning circuit. Why? If ato nang i-redraw from this form to another form, okay, I think dili siya, I think obvious man sa inyo sad na dili siya easily ma-derivan of KCL equation, no? Because we have many nodes. So let's try to redraw this one. Let's separate the DC sources and i-bend na itong mga wires so that this could become so collector emitter portion is just the same as previous. But sa base na portion, wait. Ano? Again, didlo. Correction. Okay. So this is the equivalent circuit of our voltage divider bias transistor configuration. Yan na. So if this is our IB, no, then mag-KCL ta, ang lugar ta IB1 of IB2. No? Gilisod siya. So what do we do? What do you suggest for us to simplify this portion? No? This portion of our circuit. What available tools do we have? That's of course, now source transformation would be one good tool. And with that, either source transformation or Thevenin. No? So the only way for us to simplify this portion is for us to solve the Thevenin equivalent circuit of this voltage divider circuit. No? Actually, dali naman na siya kay voltage divider circuit. Like somehow, pangitaon na nato ang Thevenin equivalent circuit of the voltage divider circuit. No? So dali ra. And we could do that using source transformation, of course. No? So before solving, no, let's say for example, we have already obtained the values. Our voltage divider bias configuration would look like this. No? VTH and RTH. Okay? Correct, no? This is what a Thevenin equivalent circuit looks like. Replace this portion of the circuit by only one source and one resistor. Do you concur? So, if, no, if you could convert our original voltage divider configuration to its Thevenin equivalent circuit and reconnect it to the original circuit, natay circuit nga ang pag-analyze ani nga part is the same sa as if emitter bias siya. Diba? Agree? Meron na siya emitter bias configuration. Then, ang analysis. No? Question next is, what are the values of VTH and RTH? Okay. So, back to dire. What is the value of RTH? Okay, ends. For Thevenin equivalent, what do we do with a circuit, with a voltage source? No? A short or a open? Thevenin. Short. Okay, so short ni. So if we're going to short VCC, no, let's try to imagine this is a plain wire. No, we have two parallel resistors, RB1 and RB2. No, and that is the value of RTH. RTH then is just the parallel resistor between RB1 and RB2. Okay. How about VTH? So if mag-source transformation ta and convert na to into this one, long story short, okay, you could derive it, pero VTH should be equal to just the voltage drop between resistor 2. No? Muna mo gawas nga na VTH, the voltage drop between PR2. No? You could perform actual Thevenin to derive this one. Basta kasi VTH should be equal to VCC times RB2 over RB1 plus RB2. Okay. Now, even if mag-source transformation punta, mo ni siya magawas nga value for our VTH. Kaya siya ma-memorize, no? Because RTH should be equal to just the plane parallel of RB1 and RB2. And VTH is the voltage drop of RB2. No? So, voltage divider niya nga portion. Okay. And balik na po sa itong KVL equation. VTH minus IB RTH. No? The current mo flow to RTH is IB. So, instead of VCC, VTH na. VTH minus IB RTH minus BBE minus IB RE is equal to 0. Okay. And the same ra gyapon diri sa PCAS, no? So VCC minus ICRC minus BCE minus IE. Ay, dapat na siya. IE RE is equal to 0. Okay? Sige, last example. No, to know kung na-learn ba na to. Okay. Given this one, BCC is 16 volts, beta is 80, RC is 3.9K, 3.9K, RC, RE is 0.68K, 9.1, and 62. Okay. Sige. On your own, try to solve for the currents IB, IC, and IE, and VCE. Sige daw. IB, IC, IE, VCE. Sige daw.